Hi, in this video we are going to talk about tail recursion. To understand the concept of tail recursion, let us first take a closer look at these two functions. One of these functions will take less time when run for slightly larger input, and the function that takes less time is this one. Let's see what these functions do. This function prints numbers from n to 1. It first prints the nth number, then recursively calls for n minus 1 numbers. This function prints numbers from 1 to n. It first prints n minus 1 numbers using recursive calls 1 to n minus 1 and then prints the nth number. These functions are written in some pseudocode where print n means cout n in C++ and system.out.println in Java. Now can you guess a reason why this function would take less time on modern compilers? Let us take a closer look at execution flow of these two functions for n equal to 3 and let's observe the difference. Here when you call it for 3, it prints 3, then calls for 2, then prints 2 and then calls for 1, prints 1 and calls for 0. Now when fun0 finishes and fun1 gets the control back, fun1 does not have anything more to do, right? So fun0 finishes, fun1 can finish immediately, and this is what is the point here in tail recursion. A recursive function is called tail recursive when the parent function has nothing more to do when the child function has finished. In very simple words, a function is called tail recursive when the last thing that happens in the function is recursive call and nothing happens after that. If you take a look at this recursive function, it's not tail recursive because fun3 calls fun2, fun2 calls fun1, fun1 calls fun0, and now once fun0 finishes, fun1 has to do something more. Fun1 comes here and prints 1, and when fun1 finishes, fun2 comes here and prints 2. When fun2 finishes, fun3 comes here and prints 3. So when the caller has to do something more after the child call, it's not tail recursive. And when caller has nothing to do after the child call, then this function is tail recursive. Basically, last thing in the recursive function is the recursive function call. Now, what is the advantage of this? Why is this function execution faster? The point is, your caller does not have to save the state, because in recursion or function calls, what happens is caller's state is saved, then called function is called, and once the called function is finished, the caller resumes execution from that same point. We don't need to resume the execution here at all. There's no point resuming the execution, and that's what the optimization that modern compilers do. So when modern compilers see such a recursive or tail recursive function, what they do is they realize that last thing is recursion call. It's a tail recursive function. So they change such functions. The changes that they make are they change this line to n equal to n minus 1, right? And then they add a go to start, and they add a label start. These are the changes they make internally. So whatever parameters you are passing in the recursive calls, these parameters are changed and this line is replaced by these two lines and then go to start. So they remove recursion completely. There's no need of recursion. And you can notice that if this function was recursive and suppose this optimization was not done, what would have happened? You would need big O of n auxiliary space for the recursive function calls. You need to store the states of the functions and then you need to resume for those states. All that overhead is gone, right? Because it's no more a recursive function. It's go to this label and this label say begins the execution again from here. So you're just changing the parameters of recursion and then you're sending the back control to the beginning of this function. These changes that modern compilers make, changing the parameter, then adding go to and then adding a label, these are called tail call elimination. Modern compilers do tail call elimination to optimize the code. Now a quick question for you. If you have a problem and if you have two recursive solutions for the problem, one is tail recursive and other one is non-tail recursive, which one you would prefer? You would obviously prefer tail recursive solution because tail recursive would be optimized by your modern compilers and it's more likely to take less time. Most of the modern compilers, they do tail call elimination and it's going to take less time. Now the question arises, if we are given a non-tail recursive code like this, can we convert this code into tail recursive? Now please pause this video and try to think of changes to this code so that it can become tail recursive. Here is equivalent tail recursive function for this function. Both of these functions are recursive and both of these functions print numbers from 1 to n. In this tail recursive function, the last thing is recursive call. So no overhead, and compiler would do tail call elimination and this would run faster. When you call this function first time, you need to pass k as 1, right? Then only it will print the numbers starting from 1. So that's an extra parameter we have added, but that gives us the advantage of having a tail recursive function. Now a quick question for you. Can we convert every non-tail recursive function to a tail recursive function? The answer is no. You can't simply convert every non-tail recursive to tail recursive by some adding extra parameters. For example, merge sort and quick sort. If you take a closer look at these two algorithms, quick sort is tail recursive and merge sort is not. And this is one of the reasons why quick sort is faster. What happens in merge sort? You first recursively call merge sort for the first half, then you recursively call merge sort for the second half, then you call a function merge. So the calling of function merge can happen only when you have recursively sorted first and second halves. On the other hand, in quick sort, you first call the function partition that partitions the array around a pivot. Then you recursively call quick sort for the left of partition and then quick sort for right of partition. So the last recursive call in quick sort is tail recursive. And apart from other reasons like cache friendliness and other things, tail recursion is also a reason why quick sort is faster than merge sort. When we study tree traversals, we'll see some tree traversals like in-order traversal, pre-order traversal and post-order traversal. If you see these three traversals, you can notice that pre-order traversal and in-order traversal are tail recursive, but post-order traversal is not tail recursive. In post-order traversal, we recursively traverse the left subtree, then right subtree, then we process the roots data. It's not tail recursive. In the in-order traversal and pre-order traversal, the last thing that we do is recursive call for the right child. And that's why when you are given a problem and if you can solve this problem using any of these traversals, you should prefer either in-order or pre-order, not to do post-order traversal. For example, sum of all nodes in a tree. So if you want to solve this problem, you can traverse the tree and find the sum, but you should prefer in-order or pre-order over the post-order. Now one last question for you. You need to take a look at this factorial function and you need to guess whether it is tail recursive or not. This function is not tail recursive. The reason is recursive call is not the last thing that happens in this function. When you call factorial n-1, you need to know the result of factorial n-1 and then you need to multiply this result with n and then you need to return. So your parent call cannot finish immediately after the child call. It's going to use the result of child call, then it's going to multiply the result with n and then it's going to return. So it's not tail recursive. Now please pause this video and try to write down a tail recursive equivalent of this function. Here is an equivalent tail recursive code for this function. What we have done here is we have added a parameter k. We initially need to pass this parameter k as 1, right? And when you make a recursive call, you do k into n. So n gets multiplied. Let's do a dry run for this function. When you call factorial for 3, right, you will first time pass k as 1 and then you will call it for factorial of 2 and pass 1 into 3, right? N is 3 and k is 1. Then you will make a recursive call for 1 and minus 1 and you will pass 1 into 3 into 2. Now when you make this recursive call, you will notice that n is 1. So you will fall into this base case. So you will return this value, which is 6. So you will return 6 to the parent will return 6 to its parent. So you finally get the output as 6. In this video, we have talked about tail recursion. It's good to have tail recursive functions because they're optimized by modern compilers and they take less time and less auxiliary space compared to their equivalent non-tail recursive functions.